What's up, everybody? We're back on Mr. Murray's Mathland, tackling another calculus optimization problem. This one, classic fencing type of problem. There's a lot of these. Sometimes they specify that you have a certain amount of fence at your disposal and you're trying to maximize the area. In this case, we have that a farmer is planning to fence in a particular set area, 6,000 square feet. Rectangular plot of land, and we're going to fence it in with aluminum fencing around the outside. The farmer also wants to install a wooden fence down the middle of the rectangle, splitting that plot into two equal size rectangular plots. And then we have that aluminum fence costs $24 per foot, wooden costs $16 per foot. Give the dimensions that will minimize the cost. Okay, right? The big question with these problems is always, what am I trying to maximize or minimize? That's what I need to make an equation for so I can use some calculus on it. And so I need to make an equation for the cost. So just a little visualization of what's happening here. We have a big rectangular plot, so let's just draw a big rectangle. Okay. And we have that the area of this is 6,000. Okay, so that's set. I'm sure we're going to be using that, right? And we have that right down the middle, there's going to be a wooden fence divided into two equal smaller rectangles. So, all right, maybe that's not exactly the middle, but you get the idea. Okay. So now it's really just up to you. There was no diagram to begin with. There were no variables. So assign your own variables if you set up a diagram, and that way any grader, any teacher can follow your work. So you can call these whatever you want. You might call these something like X or L for length, B for base, whatever. And I might call this height, Y or H, W for width. But the important thing is that there is 3 of this particular dimension, 1 for the middle and 2 for these outsides, and there are 4 of these. Or again, you might just use one big variable for the whole side. Kind of up to you, but that's why it's important to clearly define your variables on a diagram. Okay, so we are trying to minimize cost, right? So let's make an equation for what this cost would look like. The cost is going to be dictated by the cost for each of the types of fence. $24 per foot for aluminum fence, and aluminum is what's being used around the outside. So that's going to be $24 multiplied by however many feet of aluminum fence you use, and you're using aluminum around the outside, so that's going to be 2x, 2x, 2x. It's going to be 4x total, and these 2 y's on the outside, because you're only using aluminum around the outside, right? So that's going to be 24 times 4x plus those 2 y's. Plus the wooden part down the middle, the partition there, is $16 per foot. So that's going to be 16. And there's only one section that's going to be made out of that wood. So it's going to be $16 multiplied by however many feet this y is, this dimension is. Okay, so we have an equation now for the cost here. And you might like to distribute that 24. And you'll get 96x plus 48y plus 16y, because maybe you want to combine those two like terms there. 48y plus 16y, that's going to give you 64y. And so you've got yourself a decent little cost equation now, but it does have 2 variables in it, so this is where we usually use some kind of secondary condition, and that's where this area has come in if you haven't already started to think about how we're going to use that. So the area is set at 6,000. That cannot change. So think about the area of this total plot is going to be this base times this height, or 2x times y. So for this particular rectangle, 2x times y will always be 6,000. And now solve for one of those variables, either x or y, and then substitute into your cost equation to change it into one variable. So I think I will solve for y, divide both sides by 2x, and now you'll have that y is always equal to, you could actually divide that by 2 and get 3,000 over x. Okay. Now if you'll notice, I'm kind of focusing on, I've set everything up based on this one rectangle. You really could actually focus on just minimizing the cost of one of these rectangles, because this is identical to it, and so therefore you'll be minimizing the overall cost, but whatever. So in case you were thinking of going that route on your own, that would totally work too. Now we're going to substitute in. Kind of lost my train of thought there. Probably should plan these things out before I just start making these videos, but whatever. 96x plus 64. Now we're going to take out that y and substitute in that 3,000 over x in place of y. And here is really where now you've changed it all into one variable. It's kind of up to you if you want to use a calculator to help you get these derivatives, or if you feel like doing this derivative by hand. 64 times 3,000, that's going to give you 192,000 over x. I think this derivative is probably easy enough to do by hand that I might just do everything by hand on this one. So I'm bringing that x up and calling it x to the negative 1. I'm going to use a little power rule here. So my derivative, c prime, or dc dx if you want to call it that, is going to be 96. And then this is going to be minus 192,000, and that's going to be x to the negative 2, or, as I move it right back to the bottom, over x squared. So now you've got this derivative, and we're going to set this equal to 0 to obtain any critical numbers here, those potential relative maxes and mins. This would also be undefined at x equals 0, but obviously x can't be 0 in this problem. That's just not a realistic dimension. So let's just get on to solving where this equals 0. So move that over to the other side, and you're solving where does 96 equal 192,000 divided by x squared, or in other words, where does x squared equal 192,000 divided by 96, right? Just doing a little cross multiplying, or a little switching of the two extremes there in the proportion. And as it happens, 192,000 divided by 96 does go in evenly, 2,000. So kind of nice. So x would be plus or minus the square root, but again, this is a realistic problem. X can't be negative, so I'm not going to write plus or minus, but it's not because of bad algebra. It's because I know it can't be negative. So the square root of 2,000, which does reduce if you're going without a calculator. If you take out root 400, that would be 20 root 5. Or if you're using your calculator, yeah, either one of these will give you approximately 44.721. But let's actually make sure this critical number, I only got 1, but you do always want to check. There are some problems where you get kind of false critical numbers. You're looking for a max, and what you get is actually a minimum, and it might be an endpoint kind of situation with the domain. But we are trying to find things that will minimize the cost, so let's check do a little number line testing. Checking in the c prime. 20 root 5 was my critical number, my square root of 2,000, or 44.721, however you want to operate there. And when I take something less than that, 1, who knows, pick anything. There's a lot of things smaller than that, easy. If you put 1 into c prime, you're going to get 96 minus 192,000. That is definitely going to be a big fat negative number, which means the cost is decreasing that whole time. Cost is going down, going down, going down until you get to this spot when x is that. Now when you put in anything bigger than that, that's going to make this denominator, because remember, at this spot, these two fractions are equal. So use your calculator if you like, but when you put something bigger than that here, that is going to make this fraction be less than 96. So you're actually going to get a positive when you do 96 minus that number, which means after that point, the cost is going to start creeping back up and up and up and up and up, and it's never going to come back down again. So you've got yourself a relative minimum, or in this case, since there's only one, that is the absolute minimum. So there we go. And now let's just answer the question being asked. Did it ask us for the minimum cost, or no, this time they asked for what are the dimensions that will minimize the cost. Now we have said that cost will be minimized when x is this, but now we have to find the other dimension of y. And y is 3,000 divided by x. So let's just go back in. You stay organized with your work. X is 20 root 5. So y will be 3,000 divided by that x value of 20 root 5. And then actually 20 goes into that pretty nicely. It goes in 150 over root 5. And when you rationalize that, that'll be 150 root 5 over 5, and then that actually reduces to 30 root 5. So if you want to use a decimal, check that on your calculator, or just maybe you just would use a calculator way back here and say, let's get this over with here, that this would be about 67.082. So let's just make a nice sentence here to finish this off. The cost will be minimized when x is equal to, and it didn't say how to do it, but if you use decimals, be accurate to three places minimum, but I'm going to use the exact value since I've got them. When x is equal to 20 root 5 feet, and y is equal to 30 root 5 feet. And since we've clearly labeled our diagram with x and y, that is perfectly acceptable to just say x is that. If you wanted to find the overall dimensions of the big rectangle, that would also be fine, as long as you communicate clearly, label your answers, and there you go. Any questions, let me know, but hopefully that made a little sense there.